Hey everybody, and welcome back to Algebra 2 Online. So this video is kind of the start of sort of our second half of our trig unit. The first part is just kind of knowing like what the graphs of different trig functions look like, how to evaluate trig functions at different angles, like nice ones like, pi over 6 or something like that. What we're going to transition into is trig identities and trig equations. And so a lot of times what you're going to see in the real world with trig is basically you're going to run into equations where you've got to solve for some angle. And really the purpose of like this video is to show you ways that we can simplify things when we get to some equations with trig functions in them. So identities are really kind of what they just sound like. It's basically an identification between some sort of trig expression. So over here, sine squared theta plus cosine squared theta, and the number 1, right? We actually saw this one at one point, and I'll talk about actually where it comes from here in a second. But this is another famous trig identity, and this is another famous trig identity. And these three make up what we call the Pythagorean trig identities. And so what we really use this for is it helps us simplify different trig expressions and equations and things. So if you ever get some sine squared plus cosine squared thing in the same equation, like added together, what this says is since those equal 1, you can just simplify your equation and just take those out and put a 1 in place. If you ever have a 1 plus cotangent squared, you can take that out and put a cosecant squared. So typically you would use these so that you would take more complicated side and like you would write it with the 1 here, or write it with the cosecant squared or the secant squared. But you can like manipulate these, right? Like take this one, you could say, okay, well, based on what I have up there, 1's going to equal secant squared theta minus tangent squared theta, right? So you can kind of play around with these and like move things around. And so if you ever got that in an equation or something, that would simplify to 1, which is way easier, right? So there's different ways that you use these, but you basically would never want to make things more complicated, except for a few cases here and there. But so what I want to start with is just kind of reminding you where this one comes from, and then it's pretty, I think, easy to see where these next two come from. So this came out of, basically, you can think of it as the equation of a circle. So if you have, I'm going to draw a little unit circle over here. So let's say you have a unit circle. So this is length 1 right here. We can think of these like a triangle in here, right? And we can think of, this as just some x distance, this as some y distance, and we know that the radius is 1 in this triangle. And, we know that basically since x squared plus y squared equals the radius squared in a circle, right? We have x squared plus y squared equals 1 squared here is the radius, right? Is 1. But we also know that we've seen this thing where x equals, 1 cosine theta, right? Because if you take cosine theta, it's just x over 1. So cosine theta is equal to x. And then likewise, y is equal to sine of theta. So no matter where you are in that circle, if you take any triangle, if you do, opposite over hypotenuse, y over 1, it says y is sine. And so now what you can do is you can go plug these in for x and y, and you'll get the sine squared theta plus cosine squared theta equals 1. So that is, really where this one comes from. And this identity, you can get really quickly, right? If you take sine squared theta plus cosine squared theta equals 1, right? So let me write that down. And if you just divide both sides by, so the way I think about it is, what do I have to divide 1 by to get cosecant squared, right? And it would just be sine squared, right? We know if I divide by sine squared theta, right, on both sides, it should still be equal, right? And then, sine squared theta in here is a 1, but then cosine squared over sine squared is cotangent squared, right? So this is going to be 1 plus cotangent squared theta equals cosecant squared theta. And then, you got this one. And you do the same thing for the last one. If you take sine squared theta plus cosine squared theta equals 1, and this time if you divide by cosine squared on both sides, right? Sine squared over cosine squared is tangent squared. Cosine squared over cosine squared is a 1. And then 1 over cosine squared is secant squared, right? And so here it's written 1 plus tangent squared, but of course that's the same thing. So these three are really just related. And they really just relate back to Pythagorean theorem. That's why they're called the Pythagorean identities. Basically, you think of it as a squared plus b squared equals c squared. These are the legs of the triangle, the x and the y here, the legs of the triangle. And 1 is the hypotenuse, the c in the triangle, right? And then you just get this and this, but just by dividing by a certain trig function. So these three are basically all we're going to worry about today, but there's actually a whole bunch of trig identities out there, and we'll learn about some other ones down in other videos. But today I just want to work with these and show you kind of why these can be super useful. So one of the things that your homework is going to basically ask you to do is to verify certain trig identities, okay? So when I say verify tangent theta times cosine theta equals sine theta, what I mean by that is basically manipulate one side of this and show that you can get to the other side. And the way you want to do this kind of thing, sometimes we call this proving trig identities. We're basically proving that these two things are equal. But the way I would recommend you do this is always go from the complex side. So here, certainly this product is the more complex side, and go to the more simple side, okay? So here I would manipulate this and get to sine. And this one, you might be kind of sitting there already knowing how this works. But tangent theta times cosine theta, right, we can do tangent theta is sine theta over cosine theta. That's just something we know about tangent, sine over cosine. And then, this cosine is this cosine. And then, those two cancel, right? And so they equal sine theta. And we're done. So we've just shown that this is equal to this. And again, why would you care is a very important question. What I might run into in a problem is I might have this tangent theta times cosine theta equals, 1/2, okay? If I didn't realize that tangent theta cosine theta equaling 1/2, it can be simplified. It looks like a more complicated problem, but this can be simplified to sine theta, right? And now sine theta equals to 1/2, right? Now we know how to answer this. It could be like, okay, well, 30 degrees works plus multiples of 360, and then also 150 plus 360n, right? So these kind of angles are what make this equation true, because this thing has simplified to this, and this is a much easier equation to solve. So that's kind of the idea with these things. All right, just another example. So here, again, if I want to verify this trig identity, I'm going to take this more complicated thing and show that it simplifies to this thing, okay? And all the ones on the homework for, I'll talk about that in a second, like over here. All the ones in the homework are just going to utilize, at most, the Pythagorean identities. They may utilize, something like this, where it's just knowing that tangent can be written as sine over cosine. So one thing that I recommend is that when you see a squared trig function and a 1 in the same problem, like probably that has something to do with the simplification. So if you think about where you see secant squared up here, right, there's only one of them, right? And notice that if I had minus 1, right, secant squared minus 1, that equals tangent squared, right? So what I'm basically going to do in the beginning here is, since 1 equals, that sounded wrong in my head. Since 1 plus tangent squared theta equals secant squared theta, note that secant squared theta minus 1 should equal tangent squared theta, right? And that's basically what I'll just utilize here in the beginning. So secant squared theta minus 1 over secant squared theta would then equal tangent squared theta, right? That's like utilizing this over secant squared theta. And then I want to show that that simplifies all the way to sine squared, right? And another kind of common trick in these problems is to just write your trig functions in terms of sines and cosines and see what simplifies. So tangent is, tangent squared is sine squared over cosine squared. And then that's all over 1 over cosine squared. Sorry, 1 over cosine squared theta, which is secant squared theta. And then, certainly you can probably see it at this point. If you just multiply by cosine squared on top and bottom, right? That's okay to do because it's like multiplying by a 1, right? This whole thing is like equal to a 1. Right? It's a weird 1, but you can multiply by 1s. And that'll do it. So now it equals sine squared theta. So we took this thing and we got to this thing, so that verifies that trig identity. Those are equal, okay? Over here, I just wanted to kind of show you another problem where, why we might care about this, okay? So maybe I gave you that equation to solve. What I would recommend you do first is always try to simplify the trig expression. And so here, because these two things are equal, we know that this whole thing can become like literally just sine squared theta on the left now equals 1, and that's going to be a much easier problem to solve because now we're just thinking, okay, when is sine of theta equal to plus and minus 1 over root 2, right? Because if you square these two things, right, you can get sine squared, right? And so now it's just like a unit circle problem. Basically, this should look familiar as the pi over 4s, the 45 degrees, are the ones where you can get sine of that, like the multiples of that, to equal plus or minus 1 over root 2. And so basically, there's actually 4 quadrants where this can happen in the unit circle. You can have that angle, or you can have that angle, or you could have that angle, or you could have that angle. And it's plus and minus, so it can happen in the all positive, or the sine positive, or just the tangent, or the cosine. So all 4 quadrants could work here. So, we don't need to get into solving this right now. This is kind of just like a taste of where we're going with this. But, that is, I just want you to see for right now that this is kind of why we care about this. We would want to take this equation, simplify it to this, and then we'll have to proceed through the solving and talk about what angles could give you that. for right now, this is what's important. I want to make sure you know how to simplify these trig identities. All right. Just to show you one that's kind of different than the other ones. This one's different because it looks like it gets more complicated at first, but then it's actually going to become more simple. First, it gets more complicated, then it becomes more simple. And I'm actually going to solve this one out. So I'm going to find all angles that make this following trig equation true. So I want to think about, what angles theta could make 3 cosine theta plus 3 equal to 2 sine squared theta. And I'm just going to think theta between 0 and 2 pi, so one lap on the circle. Another common tip in these trig equations is try to get your equation to be in terms of one trig function. All right? That's like a good tip for a lot of these. And it might seem kind of weird how we could do that, right? We have a cosine and a sine squared. But if you think back to our trig identities here, and here, we can manipulate this one so that it looks like something regarding cosine squared, right? Sine squared would equal 1 minus a cosine squared. And so that is actually what I could use there. So notice that just based on the trig, the Pythagorean trig identities, right? Sine squared could equal 1 minus cosine squared theta, right? And that's like a weird thing to like take one term and it is not simpler, right? It made it more complicated, adding into, now you have two terms. But the benefit is everything is in terms of one trig function, and so it should be nicer to solve it out, okay? So this is kind of like another case out there. Just like any equation with, quadratic terms, like squared terms, I always recommend you get everything on one side. So I'm just going to move everything to the left, I think. So let's actually do that. So, I had to distribute here, so we have 2 and then minus 2 cosine squared. So when I put everything on the left, I'll have 2 cosine squared theta plus 3 cosine theta. And then, this is 2. Moving it over, I'll get 1 plus 1 equals 0. And to proceed further, basically, this is like a U sub problem. The way you want to think about this is basically like let U equal cosine theta, okay? If you let U equal cosine theta, then you're just going to get, 2U squared plus 3U plus 1. And now we're very used to solving quadratics like this. This one factors 2U plus 1, U plus 1. And then it's looking like U is negative a half or negative 1, okay? And then just like all U subproblems, you've got to think about what that means. This is, based on this identification, it's saying cosine theta equals negative a half or cosine theta equals negative 1. And, we're only thinking in the first cycle on the unit circle. So here, let me draw a little unit circle on both of these. So we're curious about when do we get negative a half and when do we get negative 1. The negative 1 case is pretty nice because negative 1 is right over here, right, in the x, and cosine is the x value in the unit circle, right? And so that angle is 180 degrees or pi radians, right? So we can just say theta equals pi is going to be a solution to this thing. In terms of cosine theta equaling negative a half, negative a half of the x is about right there. So we're talking about coming out to that angle. But you could also, right, come out to that angle, right? So there's going to be two of them. There could be two of them because the signs all do work out. Like if you think the all students take calc thing, sine and tangent are the only two positive ones here. And so you're definitely in those two quadrants, right? And then basically I would just use the finger trick, like having a 1 on top. You just think, cosine is square root of fingers above over 2. And so what reference angle, what finger gives me that? And it would be, my pointer finger is the only time where I have one finger above, even though it's your thumb. Your thumb's not really a finger, but so that means that this reference angle in here is like a 60. So here and here is like a 60. So 60 is, pi over 3. So this is, we're curious about that red angle, which is 2 pi over 3. And then the blue one, right, is, this would be 3 pi over 3, and then go one more, is 4 pi over 3. So theta equal to any of those would solve this equation. That's kind of a, involved trig problem right there. It uses quite a bit of stuff. You have to realize that in order to solve this, you're going to have to make it a little more complicated by using a Pythagorean identity first. Then that's nice because it gives you a quadratic form, which you can use like u sub, factor your quadratic, get your roots. Then you think back to what does u mean here? Well, u is cosine. Cosine theta is negative a half or negative 1. And then you're just doing like unit circle, kind of thinking backwards sort of stuff. And here, remember that you only are considering the first lap on the circle. So you don't want to go around and around and around and around. All right. Just one more problem I want to do. So I want to verify that this big messy looking thing actually just equals that, okay? And I have a few hints here, all right? One thing I want to kind of make clear, so take the graph of sine, okay? Sine looks like that, roughly. And if you think about it, right, sine of negative x, this is important because we have negative of the variables in here, is actually going to equal negative sine of x, right? Because if you take like this part right here, right? If you think about taking that part and flipping it, this is a horizontal flip, it would line up literally like right here. Like this point is going, here, let's make a little more clear symbols. Let's do a square there, triangle there, triangle there, something like that. So that's what we would get if we just did the horizontal flip. But so it's not lining up with itself that way, but if you then did a vertical flip, right, you would be right back to where you started, right? Because now if you take this red graph and you do a vertical flip, right, then, this part is going to go down here, this is going to go here, but you can see that it'll actually end up lining up back with where it was. So a fact about, you can call it a trig identity if you want, but it is true that sine negative x is equal to the negative of sine x. This one's probably a little easier to see because it is like an easier relationship. But if you take cosine, cosine roughly looks like that. Cosine is nice and symmetric with the y-axis. So if you do a horizontal flip, right, this, would move over here, this would move over here, this would move over here. You can see that, like, the negative in here basically doesn't affect cosine. It's symmetric on this. So it's going to be, this is really what it means to be an odd function. But anyways, that simplifies really nicely. If you ever have a cosine of a negative angle, it's just equal to the cosine of the positive angle, which is a nice thing to know. So I'm going to work with this side, and I'm going to simplify it and get to this simpler side over here, okay? So I'm going to start off and take all of this stuff and just use these facts with sine and cosine. So basically I'm going to have, so to start off, I'm just going to utilize these facts with all this stuff in here. So that first one, we are squaring sine of negative theta, but I messed up. Sine of negative theta, right, is negative sine of theta. And then the next part, we're squaring cosine of negative theta, but cosine of negative theta is really just cosine of theta, right? And on the bottom, sine of negative theta is negative sine of theta. And then cosine of negative theta is just cosine of theta. And we know that when we square a negative, right, it's positive. So that part now becomes sine squared theta. And then we have minus cosine squared theta. And then I might take out the negative 1 just because there's a negative in both those. All right. This is a difference of squares, so it's always good whenever you see a difference of squares to go ahead and factor it. So that would factor into sine theta minus cos theta times sine theta plus cos theta. And then here we have minus the quantity sine theta plus cosine theta on the bottom. And then this is nice because sine theta plus cos theta cancel, right? And we know that if we divide by a negative, that's going to be the same thing as minus sine theta plus cos theta. And we wanted to show that it equals cos theta minus sine theta, which is, of course, true, right? And so that does it. So, we took this big, messy-looking thing, and we show that it simplifies to that. So we have verified the identity. Again, we mostly just use this stuff because we wouldn't want to deal with that in an equation. We would want to deal with this in an equation. This is a much easier thing. So we would basically do this kind of work to simplify this down to this, and then it might be easier to solve something from there. That is basically the goal of a trig identity. The homework will basically just consist of utilizing at most these 3 Pythagorean identities to help us. You may also have to, pull on our knowledge of, things like tangent is sine over cosine, or something like this where secant squared is 1 over cosine squared. But you're just doing like one thing at a time to try to simplify down to whatever thing they want in the problem. So that is basically all I want to say in this video about the Pythagorean trig identity.